Right now, somewhere in Panama, a ship the length of 4 football fields is being lifted 85 feet straight up into the air. No crane, no pumps, no engine doing the lifting. Just water, moving exactly where gravity tells it to go. Here's the part that should bother you. The Atlantic and the Pacific are basically at the same sea level. So why does a ship crossing between them need to go up at all? The answer is a decision that sounds completely backwards. When engineers looked at the mountains sitting between the two oceans, they didn't dig through them, they flooded them. Decades earlier, the French had tried it the conventional way. Ferdinand de Lesseps, fresh off building the Suez Canal, tried to cut a sea-level channel straight through Panama, the same way he'd cut through the Egyptian desert. Egypt had been flat and dry. Panama was mountains, jungle, and swamp. Landslides buried the trench faster than crews could dig it out, and disease, mostly yellow fever and malaria, spread by a mosquito nobody had identified yet, killed an estimated 20,000 workers. By 1889, the French company was bankrupt, and the project was dead. When the Americans took over in 1904, they made a call that changed everything. Stop fighting the mountains. Dam the Chagres River instead, and let it flood an entire valley. That flooded valley became Gatun Lake, and when it finished filling in 1913, it was the largest man-made lake on the planet, roughly the size of Lake Tahoe. It also erased tens of miles of digging the crews would otherwise have had to do by hand. Ships wouldn't cut through the Continental Divide. They'd float over it. There was still one ridge too high for even the lake to cover, a stretch of rock now called the Gaillard Cut. Crews had to blast and dig an 8-mile gash through solid stone to link the lake to the Pacific side, and landslides kept sliding back into that cut for years after the canal opened. The lake solved most of the problem. It didn't solve all of it. Here's where the real trick comes in. On each side of the canal, a set of stepped locks, one called Gatun, the others Pedro Miguel and Miraflores, works like a staircase made of water. A ship enters the first chamber at sea level, the gate closes behind it, and a valve opens. Water from Gatun Lake, sitting higher up, rushes in through tunnels 18 feet wide, and the chamber fills in about 10 minutes. As it fills, the ship just floats upward with it. No winches, no cranes, buoyancy does the work, gravity supplies the power, and that's a choice, not an accident. Engineers could have used pumps. Pumps existed in 1913 too. They didn't, on purpose. A mechanical pump needs electricity and can break down. Gravity can't. The Canal Authority still states it plainly today. Not a single pump moves water anywhere in this system. It's the same physics that lets a rubber duck rise in a bathtub, scaled up to lift a ship the length of 4 football fields, repeating chamber after chamber, 24 hours a day, since 1914. And the gates holding all that water back? Their design isn't even from this century, or the one before it. It comes from a sketch Leonardo da Vinci drew in Milan in the 1480s, for a canal lock nobody remembers today. His idea was 2 angled gates meeting in a shallow V, pointed toward the incoming water. The harder the water pushes, the tighter the gates seal themselves shut. 400 years later, engineers in Panama used that exact same principle to build gates weighing hundreds of tons, self-sealing, using nothing but the weight of the water they're holding back. So, the ship is rising. But how does it actually move through the chamber? This is where almost everyone gets it wrong. You'll see electric locomotives, called mules, running alongside the ship on tracks, cables pulled taut. It looks like they're towing it. They're not. A canal pilot, not the ship's own captain, takes control the moment the ship enters the channel, and from there, the ship moves under its own engine power the entire time. The mule's only job is to keep it perfectly centered, using up to 8 locomotives on one vessel. In some of these locks, a massive ship has as little as 2 feet of clearance on each side. Miss that, and you don't scratch the paint. You damage a 100-year-old concrete wall holding back an entire lake. Now, about that lake. Gatun Lake isn't just scenery for ships to cross. It's the fuel supply for the whole system, and it does double duty as the drinking water source for 2 entire cities. Every time a ship crosses the canal, it costs the system roughly 50 million gallons of fresh water, used to lift it up on one side and lower it back down on the other. That water doesn't get pumped back up the hill. It drains straight out to sea and it's gone. The only way Gatun Lake refills is rain. Hold on to that detail. It's about to matter a lot. Because by the early 2000s, the canal had a size problem. The original locks could only fit ships up to a certain width, the Panamax standard that shaped the entire shipbuilding industry for a century. But container ships kept growing, and in 2006, Panama voted to do something about it. A $5.25 billion expansion, finished in 2016, adding a third lane of much larger locks. These new locks can handle ships over 1,200 feet long, carrying up to 14,000 containers, nearly 2.5 times what the old locks could move. You'd expect a chamber that size to guzzle even more water. Here's the twist: it doesn't. Engineers built 3 giant water-saving basins beside each new chamber, which catch the water on its way out instead of letting it wash into the ocean, then reuse it on the next ship. Those basins recover roughly 60% of the water every cycle, so a transit through these massive new locks actually uses about the same amount of water the old, much smaller ones did. Bigger machine, same appetite. The new locks don't even use Da Vinci's swinging gates. They slide sideways on tracks instead, with curved chamber walls that spread the water pressure out more evenly. So why does any of this still matter today? Because this 100-year-old gravity-powered machine still carries somewhere around 5 to 6% of all global maritime trade. A ship sailing between New York and San Francisco saves close to 8,000 nautical miles by cutting through Panama instead of rounding Cape Horn, turning a months-long voyage into an 8 to 10-hour transit. None of that comes cheap. A single large ship can pay anywhere from a few $100,000 to well over $1 million in tolls for one crossing, and it's usually still worth it compared to the fuel and weeks the long way around would cost. 2 decades ago, breaking the canal's toll record meant paying around $460,000. That record climbed past $800,000, then past $1.1 million. And that was before anything went wrong. Because remember that detail about rain being the only way to refill the lake? In 2023, that became the whole story. A brutal drought, worsened by El Niño, dropped Gatun Lake to its lowest levels since 1965. The Canal Authority had no choice but to slash daily transits from the normal 36 or so down to just 18. Ships queued for weeks, wait times stretched past 3 weeks at the worst point, and yearly transits fell by almost 30% compared to the year before. One shipping company got so desperate to skip the line that it paid nearly $4 million in a single auction on top of the regular toll just to get through faster. And this isn't old news. As of this summer, with a new El Niño already declared, canal authorities have started cutting how deep ships are allowed to sit in the water once again, tightening the rules for the largest vessels just weeks ago. So here's the thing that makes the Panama Canal genuinely remarkable. It doesn't run on diesel, or electricity, or oil. It runs on rain falling over a rainforest in Panama, and on a design of angled gates a Renaissance painter sketched 500 years before the first container ship existed. That same elegance, 0 pumps, all gravity, is exactly what makes it fragile. The ship you pictured at the start of this video, the one being lifted 85 feet by nothing but water, multiply that by roughly 35 vessels a day, every single day, and you start to see exactly what's riding on a good rainy season. The single most important shortcut in global shipping is, at its core, completely at the mercy of the weather. If a trick this simple can move 6% of the world's trade, what do you think happens the day it stops raining enough? Let me know what you think in the comments. And if this kind of hidden engineering fascinates you as much as it does me, there's a lot more where this came from.